So if you're getting into the second portion of your Calc 1 course or your AP Calc AB course, you're going to start talking about finding summations. You're about to define something called a definite integral, and in order to define that successfully and be able to work with that definition, you have to be able to deal with summations. So we'll talk briefly about sigma notation, summation formulas, and then final example here will show what is involved with what's called a change of index. So if we have a summation, it's denoted mathematically with the capital Greek letter sigma. So the index here is I. I is beginning at 1 and I is ending at n. Now, this particular summation that you see in numeral 1 here is just adding up a bunch of constants. So if I was to add up a constant n times, the way that I can compute that sum is c times n. That should make a decent amount of sense. So this summation formula that you're seeing at the top is going to make the most sense. I'm not going to necessarily take time to prove numeral 2 or numeral 3 here. You can prove that with a process called mathematical induction. You can probably seek out other videos on those. We'll just go ahead and check out what these next two formulas are saying. If you're taking the sum from 1 up to n of I, this would be 1 plus 2 plus 3 plus 4 plus 5 up until whatever value of the index sits up here. The shortcut for computing that sum is to take where the index ends, multiply that by that value plus 1, and divide by 2. And if you're adding together the sum from I equals 1 up to n of I squared, so 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared, the shortcut for computing that sort of sum is to take where the summation ends, n, multiply by one value above that, multiply by double where it ends, plus 1, and divide by 6. Again, the process of mathematical induction can be used to prove where these come from. That's not necessarily the point of this video. We'll jump down to this, and then we'll show a couple examples and wrap this up. So this theorem that you see at the bottom here, it says for any constants c and d, if you have a sum from 1 up to n, and again, this capital Greek letter sigma is what indicates a summation, we have a constant times a certain rule that's going to involve the index, plus another constant times another rule that might involve the index. We can actually break that up into two separate sums that are added together, and those constants can be factored out in front of those sums. So when you're learning these in your calculus course, you'll probably do some problems like the one that you'll see here. So if I'm trying to compute the value of this sum from 1 up to 140 of I squared plus 2I minus 4, one way that I can do that is I can put 1 in place of the i's, figure out what my value is. I can then put 2 in place of the i's, figure out what that value is. Put 3 in place of the i's. That process is going to be kind of lengthy because I'm going to have to keep upping the index by 1 unit until I get to 140, and then I'm going to have to add up all those values. That direct approach is not wrong, but that is definitely time consuming. We can take advantage of what we just talked about on the last screen in order to speed this process up drastically. So I can break the addition and the subtraction up into multiple summations, right? The bottom property on the last screen said that. And I can factor this constant 2 out in front of that other summation. Now, if you look at this first summation here, the rule for it is simply I squared. If you look at this summation here, the rule inside of that is just I. And if you look at this last summation, the rule is just a constant value 4. Why is this breakup from top line to this line beneficial? I have the opportunity to apply this formula, I have the opportunity to apply this formula, and I have the opportunity to apply this one. So how do I go about doing that? Well, the sum from 1 up to 140 of I squared, this summation ends at 140, so I'm going to take n, 140, times n plus 1, 141, times 2n plus 1, 140 times 2 plus 1, divide by 6. That's a direct application of the formula that you see here. Next, I'm going to apply the one that you see in the middle. So I copy this 2 in, and then that middle formula is going to say I take where the summation ends, 140, multiply by one value above that, 141, and divide by 2. And then the first formula that we saw on that last screen said if you just have a constant as the rule for the summation, you're going to be able to find that summation by taking whatever the constant value is and multiplying by where the summation ends. Now this calculation here is not that nice to do with just arithmetic, no calculator. It's not impossible to do, but it's definitely a little bit time consuming. So I definitely fired up the calculator to get this result. For those of you that are gearing up to define a definite integral, you'll not necessarily do problems like this one when you do that. These problems are designed to get you familiar with the properties of summations and these formulas that we're using, and you'll eventually be doing limits of calculations that look like this one. If you look at this last example, it's the same rule for the sum, I squared plus 2i minus 4. But if you notice, the index of this summation does not start at 1. It starts at 4. So how am I going to be able to use these formulas, which all require my index to start at 1, if my index does not start at 1? Well, one way to compute this sum is to put 4 in place of the i's, figure out your value. Put 5 in place of the i's, figure out your value. Do the same thing with 6, 7, 8, 9, 10. Do that with everything up to 140. Add them all up, you've got your answer. Not quick, not easy. I guess it's not too bad, but not quick. Definitely time consuming. So how can I adjust this lower value of the index to begin at 1 rather than at 4? Well, this process that we're going to go through is called change of index. And there are alternates to this, but for those of you that are in a spot where your professor's requiring for you to do pretty involved work with summations, this is a pretty useful technique to know. So what we're going to do is we're going to literally change the index from I to some new letter. I'm picking K. And what I want to do is I define K. I want K to begin at 1. I want to unlock the opportunity to use those formulas. In order to use them, my index must begin at 1. So what I'm going to do is I'm going to define K to be equal to I minus 3. Why is that useful? Well, if K is I minus 3, when I rewrite the sum, this is a value of I. 4 minus 3 means that K is going to begin at 1. This is also a value of I, 140. Well, when I transition that to the appropriate value of K, 140 minus 3 causes this new summation to end at 137. The one step that I see students oftentimes forget to take when they use this change of index process is they think, all right, I've got what I need here and here. Now I'm just going to copy this rule. You've defined K in terms of I. You're going to have to replace I, or whatever the original index is, you're going to have to replace that appropriately. So this equation here is pretty easy to manipulate and figure out what I is equal to. I just add 3 to both sides. I is equal to K plus 3. So what you'll notice, I put K plus 3 in place of the I that was being squared. I put K plus 3 in place of the I that was being multiplied by 2. And then I just copied in the minus 4. Now, we are in a spot where we're going to have to do a little bit of algebra before we can use those formulas from a few screens ago. So I can't distribute this exponent, but I can write K plus 3 times K plus 3 and expand that, and you should get K squared plus 6K plus 9. I can distribute this 2 into that set of parentheses, getting 2K plus 6. The minus 4 is just going to copy down. Got some like terms. The 6K and the 2K will give me 8K. The 9, the 6, and the 4 minus 4 are going to combine to 11. K squared just copies in. Now this is very similar to the last one. I can break it up into 3 separate sums. I can factor 8 out in front of that middle sum. And I know this is not I anymore, it's K squared, but I've changed the index to a different variable, but I still have the opportunity to use those summation formulas. So on this last screen, what you'll see is I took 137 times 1 above that, times 2 times 137 plus 1 divided by 6. I added on the constant that we factored out, 8, times where that summation ended, times 1 above that divided by 2. I've added on 11 times 137, and then I tossed that into the calculator to get my value of 943,656.